This lecture is from chapters 10 and 11. In chapter 10, we're going to be looking at correlation and regression. I'm not going to bore you by reading the text to you, but I do want to talk about the concept of correlation. A correlation exists between two variables when the values of one variable are associated with the values of another variable. And you have a linear correlation between the two variables when there is a correlation between the variables and the graph is approximately linear. Sometimes when we plot, let me see if I can get this to cooperate with me here, just to give you an idea of what's taking place here. Sometimes when you plot points, let's say that you're plotting the hours someone spends studying the ACT. I'll just use a T there for time. And let's look at their ACT score. And suppose we look at 5 different students. We'll just keep it small for the sake of argument. And, we notice that one student studies for the ACT for 1 hour, and that student happens to score a 16 on the ACT. So we'll plot their point here. And the second student, make that a little darker, perhaps. The second student we look at studies for 2 hours and scores a 17. So we would plot that student's point here, let's say, and we do this for 5 students. We look at the amount of time they spent studying for the ACT, and we compare that to their score. Okay. Now, if we look at the graph, it appears to me that the longer a person studies, in other words, as time moves to the right, the longer a person studies, the higher the score. Let me see if I can switch colors. In fact, I can sort of visualize a line that could pass through the points, and that line would be fairly close to these data values. Now, obviously, if these data values lined up perfectly, we would have no gaps between the red line and the blue data points. But if we look at this, it appears to be fairly linear. If they were exactly linear, then I would have a correlation coefficient R value of 1 if the graph is positive. In this case, this line is positive. So I'm pretty close to 1, I will argue, because the points are almost linear. If you have a situation where the R value is 0, well, if you have an R value of 0, that basically means that your points are all over the place. There appears to be no linear correlation at all. And if you happen to have an R value that's close to -1, they would still be fairly linear the closer you get to -1. But as you can see, they're going down. The closer you are to either -1 or the closer you are to 1, that determines the strength of the correlation coefficient, the strength of the line, the linearity of the line. So the closer you get to 1 or -1 for the R value, the more linear the data values. Okay, let's see if I can erase these for now so they don't stay with us as I move the screen. So I hope that gives you some idea of the importance of the R value. And if that is not clear, then hopefully by the time we get through a couple of examples, it will make better sense. So let's go right into example 1. Consider the following data on shoe sizes and height. And these measurements are in centimeters. And we want to know, is there a linear correlation? First, we're going to enter the data in lists 1 and 2. Then we're going to use stat tests, linear regression t-test. We're going to test whether or not there is a linear correlation between shoe size and height. So pause the video and go ahead and enter the information in L1 and L2. It's very important when doing linear regression that we make sure that we keep the corresponding shoe sizes and heights together. We do not want to interchange these. So keep those respective of one another. And we're going to use an alpha level of 5% since an alpha level was not assigned to us. We'll use the default. Okay. First, let's write the null and alternative hypotheses. The null is going to claim that there is no linear correlation, and the alternative is going to claim that there is a linear correlation. If you run stat tests, linear regression t-test, and you input the fact that you're using lists 1 and 2, you will generate a p-value of 0.2937. Well, 0.2937 is larger than the alpha level of 0.05. And anytime the p-value exceeds the alpha level, we fail to reject the null. Since we have failed to reject the null, our conclusion is that there is not enough evidence to support the claim of a linear relationship between shoe sizes and height. Okay, notice that the calculator assigned an R value of 0.5912. Well, it's positive, but 0.5912, let's see, if this is 1 and this is 0, 0.5912 is going to be slightly above half. So it's not close enough to R in order to see a linear relationship, or at least one that is significant. Example 2. Consider the table that shows customers' bills and the amount of tip they leave. So let's say you are a restaurant manager and you collected several bills. And let's say you happen to randomly select the bills and you took note of the tips that went with each bill. For example, there's a bill of $50.68. The tip was $5. There was one for $63.60. And the tip was $12, and so on. I want to know if there is a linear correlation between the amount of the bill and the amount of the tip the customer leaves. Again, I would suggest at this point that you pause the video and you enter the bill amount and the tip amount in L3 and L4. And again, make sure that you correspond each bill with its requisite tip. Let's write the null and alternative hypotheses. Again, the null is going to claim that there is no linear relationship between bill and tip. The alternative is going to claim that there is a linear relationship or a linear correlation between the bill and the tip. If you go back and run the linear regression t-test, we get a p-value of 0.04. Well, 0.04 is less than 0.05, our assumed alpha level. And anytime the p-value is less than the alpha level, that means it is inside the tail region, and we will reject the null. So the conclusion would be that there is enough evidence to support the claim of a linear relationship between the bill and the tip. And notice this time the R value is 0.83. So 0.83, if I can go back up here to this diagram, let's say that 0.83 is going to be a lot closer to 1. It's not a perfect line, but it's perfect enough to allow us to use a model to predict tip values based on the bill amount. Example 3. Example 3 is a reference back to example 1. That was the problem that dealt with shoe sizes and heights. If you'll recall, we found that there was no linear correlation between shoe size and height. So what happens if you would like to estimate the height of someone if you know their shoe size is 30? Since there's no linear correlation, we really can't graph this in a meaningful way that allows us to make a prediction. The best we can do at this point is to go back and look at our list of heights and average those together. Take the height average, and that's the best you can do. So if no linear correlation exists, the best estimate is always the average of the data. So to get that average, I would just put the heights into a list and run one variable stats. Example 4. Now example 4 refers back to example 2. Remember in example 2, we did find a linear correlation between the customer's bills and the amount of tip that they left. Since we trust this model, we are going to actually use the regression equation to predict. So let's estimate the tip for a $58 bill. Let's rerun the linear regression t-test as before. And this time, if you look on the calculator, near the top, it will tell you that the regression equation is y is equal to a plus bx. That looks a lot like slope-intercept form from algebra. And it essentially is. To the nearest 4 decimal places, what are the values of a and b? Well, notice that a is negative 0.3473 and b is 0.1486. If we substitute those values in for a and b, the regression equation is minus 0.3473 plus 0.1486x. So what does that mean? It tells me this. The customers are tipping in this manner. They're basically close to taking the bill amount, which is x, multiplying by 0.1486, and then they're subtracting about, let's say, 35 cents. So these customers are tipping somewhat close to 15%, maybe a little less. But we trust the model because of the p-value. Since we trust that model and we found that there is a linear correlation, if the bill is $58, then we can predict a tip amount of about $8.27. Now, how did we get the $8.27? The variable is the bill amount. So we would plug in 58 for x, so 0.1846 times 58, and then subtract 0.3473, and we get $8.27. So if your customers continue to tip along this model here, in other words, they're very predictable, very stable, you should be able to tell what your employees are earning in terms of tips. A couple of points here before we move on. Point 1, remember, if no linear correlation exists, average the data values to estimate a particular variable. Point 2, if a linear correlation exists, use the regression equation to estimate a particular variable. And that is exactly what we did here. we found that we did have a linear correlation, and therefore we used the regression equation to estimate a particular variable. In this case, we estimated the amount of tip that would occur on a $58 restaurant bill. Chapter 11, chi-square test for independence. I just realized I have an error on here. I'll have to take care of that momentarily. So for example 1, are automobile accidents independent of automobile color? In other words, does the color of your vehicle affect the probability of your having an accident? So let's investigate and see. The null is going to claim that accident rates across vehicle color are independent. In other words, the null hypothesis is basically claiming that it doesn't matter what color your vehicle is in terms of whether or not you're going to have an accident. The alternative hypothesis is going to claim that they are dependent of one another. So the alternative hypothesis believes that the color of your vehicle does determine the probability of your having an accident. So let's see who's right here. If we look at the table, we have 3 vehicle colors. We have black, white, and red. And we basically surveyed the drivers of these vehicles and said, hey, have you had an accident in the past year? Some said yes, and some said no. That gives us this table of values here. We're going to disregard the marginal values. They're not going to be needed. I'm just going to go straight for the raw data here. Notice that I have a 2 by 3 matrix because I have 2 rows, yes and no, and then I have 3 colors for the vehicles, right? Black, white, and red. So this is a 2 by 3 matrix. Now somewhere in my haste, it appears that I actually did 2 by 4, but that actually should be a 3. So let's scratch that out. And it looks like I did the same thing down here. Don't want to confuse you, so let me get that fixed. Okay. Again, if you look at the raw data values without the marginal totals, this would be a 2 by 3 matrix. So here's what we're going to do to test for independence. Select second function, x inverse, which takes you to the matrix menu. And your calculator should default to edit A, which means that's going to be matrix A. For simplicity, I would suggest that we always use matrix A. Once you get more accustomed to doing these types of problems and you can use other matrices, that's fine. But for learning purposes, let's stick to using matrix A. So after you select second x inverse and go into the matrix menu and choose A, we have to, let me clear this off. Okay. You have to enter the values into the matrix. So you will enter on the top line 420, 147, 246. And then on the second row, you will enter 278, 573, and 70. After you enter those values, press Stat, Tests, and you are going to run the chi-square test, also known as the chi-square test for independence. Then you're going to calculate. Once you calculate, you are going to see the test statistic. So the chi-square test statistic is 373.69. But notice the p-value is 0. Now don't think that the p-value is larger than 1. Notice at the very end you have e followed by some number. Well, that means that the p-value is pretty much 0. A p-value that's pretty much 0 is going to be less than an alpha level of 5%, and anytime the p-value is less than the alpha level, we reject the null. Since we have rejected the null, what does that mean? It means that the color of your vehicle and the likelihood of an accident are dependent on one another. The color of one's vehicle may influence the probability of his or her being in an accident. I would avoid the red vehicle. Something tells me that people who drive red vehicles are more likely to be in an accident, but I could be wrong. Example 2. The table below shows survival rates on the Titanic according to age and gender. So this is a test to determine whether or not someone being old or someone being young, male or female, did that determine the likelihood of their surviving or not? Well, if we look at this chart, we see that we have two categories of people based on survival. Some survived and some died. We have men, women, boys, and girls. So we have 2 rows, and we have 1, 2, 3, 4 columns. This one is a 2x4 matrix. And we just go through the same process. The null is going to claim that survival rates according to age and gender are independent. And the alternative hypothesis is going to argue that age and gender across survival rates are dependent. In other words, the alternative hypothesis is basically saying, look, the age you are or the gender you are does affect whether or not you're going to survive this incident. Go ahead and enter into the 2x4 matrix. You will have to change your parameters to 2x4 instead of the 2x3 we used before. Once you enter the information into the matrix, run the chi-square test for independence. This time the chi-square value is 507.1. And again, the p-value here is pretty much 0. And since a p-value of 0 is less than an alpha level of 5%, that means that the p-value does fit inside the tail region, and we will reject the null. So what does that mean? It means that one's surviving the Titanic's sinking was affected by their age and gender. Because the null at the very beginning argued what? The null would argue that they are independent. But since we have rejected the null, we now know that survival rates by gender and age are dependent. If we were to examine a little bit closer, we would find out that women and children did have a higher survival rate than adult men. But to figure that out, you have to run a special test, which is beyond the scope of this lesson. So hopefully these examples helped you to get a better understanding of linear regression and the chi-square test for independence.